The title of our project is Design and Analysis of Higher Efficiency Compressor Blade. This is my team, Akchhara, myself Akhil, Jason, and Olivia. We are supervised by Professor Richard Sandberg. A compressor is a device used to increase the pressure of a gas by reducing its volume. Compressors are used for various industrial applications like pipeline transport, aircrafts, to power pneumatic tools, etc. They are also used in our day-to-day lives like HVAC systems, blow dryers, and much more. A large contribution to ensuring high efficiency is in minimizing aerodynamic losses, which are mainly driven by the interaction of the flow with the blades. The overall loss generated by a compressor blade can be inferred from the wake profile measured downstream of the trailing edge of the blade. To simplify such measurements, static blades are used rather than rotating blades. The scope of the project was rescoped from design and build to design and analysis of high efficiency compressor blade due to the lack of access to university workshops. The aim of this project is to design and analyze the efficiency performance of smooth surface compressor blade, of which the geometry is supplied by our industry partner Dyson, in a linear cascade simulated through computational fluid dynamics, Reynolds average Navier-Stokes analysis. The blade design will be focused on the ease of manufacturing techniques through interchangeable parts of the blade responsible for the surface texture.
The previous year's team had successfully manufactured the experimental setup, which included a diffuser, settling section, test section, and blade cascade. The aim of the project was to experimentally validate the simulated results obtained for Dyson by Willsby. The team conducted tests for a range of AOIs, that is, angle of incidence, and velocities, but were unable to conclusively verify the trends observed in the theoretical model. The previous year's team recommends a few tasks, like reducing the bulkiness of the model, validating their results by use of smoke, and finding better ways to manufacture the blades. The course of action taken by the team was to first study the previous year's reports and do a literature review to familiarize ourselves with the concepts. The blade was designed using the geometry provided by Dyson, followed by the addition of the chevron pattern. It was then decided to add the feature of interchangeable patterns to the blade for future use. CFD analysis was run simultaneously to study the wake losses and use these pressure readings from the simulation to perform FEA analysis on the textured blade. Studying the FEA and CFD results, the team intends to propose the future work and recommendations.
I will talk about our blade design. Initially, we received the 2D plot of the blade, but we need to determine our desired dimensions by ourselves. In the lab, we measured the width of the wind tunnel, which is 600 mm long, and it should be equal to the span length of the blade. Besides, in the project, we assume that the desired chord length is 3 times shorter than span length, so it should be 200 mm. In the plot, the chord length is 31 mm, therefore magnification factor is about 6.5, and hence we can calculate the thickness of the blade. Once we know both geometry and the dimensions of the blade, we can create smooth blade using AutoCAD. And for texture blade, the only thing we need to do is placing some interchangeable patterns on the surface of the blade.
Computational fluid dynamic simulation was run through a program called OpenFoam, utilizing the K-Omega SST turbulence model to solve the Navier-Stokes equation. The simple foam solver was utilized, which is the steady-state solver for incompressible turbulent flow. The initial conditions imposed in the CFD case are in reference to the values experimented by the previous year's capstone team of a low velocity of 3.3 meters per second. As we are evaluating a single compressor blade, a pipe cyclic boundary condition has been imposed to mirror the environment in which the blade sits in, a compressor. Here you can see the wake developed by the blade. We can see that velocity at the wake is much lower compared to the free stream velocity. Conversely, the pressure in the wake of the blade can be seen to be higher, consistent with Bernoulli's principle. These results are also consistent with the expected behavior of a compressor blade. The velocity from the wake can be seen in this plot here, where the data collected corresponds to the distance from the trailing edge of the blade, which are 20, 25, and 30% of the chord length. Similarly, the wake loss or the pressure loss can also be plotted to enable a better understanding of the blade's performance.